Okay, so I actually got a little bit of light in here because I realized I moved my office around a little bit to be more accommodating to the cats, and so and then I noticed, well, now I can't see the hummingbird feeder that I put there, and I got these two hummingbirds. They're so cute and really pretty, and anyway, so I opened the blind a little bit, and so now everybody's happy. The cat is happy. I can see the hummingbirds, and so everything's good. And we're making our way through 5.3, and we're trying to decide which one would be the best to use. 5.3 is by far of the sections because it has both 5.2 and 5.3 problems in there. They kind of get mixed together. And where I took these problems from were not your textbook, but from problems that I had on the test from a previous semester. So that's where my problems are coming from. And so it says here, and in fact, I think I might have even taken some problems from several tests. It was like, I need more examples that are already typed up. And so that's where I got them. Okay, so find the volume of the solid obtained by rotating the region bounded by the given curves about the specified line. So y equals x to the third, y equals 0. So I'm going to sketch this. Y equals 0 is the x-axis. So there I am on the x-axis. X equals 1 is here. Now, I know where this is crossing, right? That was a question I have been asked, is how do you know where these things are crossing? Well, the two equations are y equals x to the third and x equals 1. And so when you put in x is 1 in here, you get y is 1, right? And so it's crossing where x is 1 and y is 1. And so right here, and 1 right here. So it's always possible to find where they're crossing. You might have to solve equations, or it might be like this one where I have to solve. So this is my solid that's going to be rotated. And so this is not going to be part of my solid, so I'm going to erase it off of here. And it said about the line x equals 2. So here's x equals 1, here's x equals 2. So that's parallel to the y-axis. So if I'm going to use a disk washer, it's going to be dy, which means your equations need to be solved for x. X equals blah, blah on your equations. And I certainly can solve these equations for x. That would be easy. Not this one, but the ones that have x in them, I can solve them for x. That would be easy enough if I wanted to use the dishwasher method. I certainly could. We might investigate that even. If I want to use the shell method, then that would be dx, which would mean your equations need to look like y equals blah, 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 right? And they certainly already do look like that. So maybe I'll use the shell method on it. I might just set this one up and do it both ways. And so anyway, so a long story short, if I decide to use the shell method, just going with what it is, then I need to identify what h is. So that's what I'm going to be thinking here is, what is h? And a lot of times when your equations solve for y, that h is top curve minus bottom curve. And certainly, so here, remember, parallel to the axis of rotation, so the axis of rotation. So this is a typical h. Right there. There's h. A typical h. This pen skips out. And so there's many h's, and all of my h's go between 0 and 1. So we already know our bounds, 0 to 1. And so that's a typical h. The top curve is x to the third. The bottom curve is y equals 0. So x to the third minus 0. So h equals x to the third. And then r equals, now this is the distance r, right? R goes from the axis of rotation to H. And I always draw it at the point that I have right there. Now, what I know is that this distance from the y-axis rather, to that point is called x. Always, that's the distance x, right, over x. But that's not what r is this time. And so all the other problems that we had going about the, we had them going around the y-axis. So r would have just been x if I had been going around the y-axis. But since I'm going around the line x equals 2, that's not what r is. But it does give me a way of finding r, because I know that x plus r equals 2. This distance, oh, there's my hummingbird. This distance is 2. And I know that x plus r equals 2. I want to know what r is, though. R must be 2 minus x. So right here, 2 minus x. And now I'm ready to put this together, right? So the volume for a shell, so the shell, the volume is 2 pi. So I'll put the 2 pi in the front. R, which is 2 minus x, and then times h, which is x to the third, dx. And then I just have to get my bounds on there. We said they were 0 to 1, so boom, 0 to 1, and then I'm done. And they're 0 to 1 right here. Here are my bounds right there, 0 to 1, right, for in terms of x. And so then if I wanted to solve this, I would multiply this together and solve, right? So that's how you would set it up as a shell. And I want to show you, so solve, that, hey, this problem could be done as a disc washer. And sometimes it's the same amount easy, and sometimes it's harder, one method versus the other method. So we'll see what we think it is. I'm going to draw it in here. So we had this, and this height happens to be 1 as well. Coincidental, right, that these are both 1 because of the equation that we have. So if we decide that we're going to use the disc washer, I think dishwasher when I say that instead of the dishwasher, then what we know is that we need our equations to be solved for x. They need to look like x equals, and in order to use the dishwasher. So the main equation that I have, I need to take the cube root of both sides. So this would be x equals the cube root of y, okay, which is the same as y to the 1/3. And so, so let's see here. We need to get my axis of rotation on here. Where was that at? It was at x equals, what was it? X equals 2. So this is x equals 2, and it's the axis of rotation. Okay, and so now we want to draw our typical R's on here to decide if it's a washer or if it's a disc. So you always start with the axis of rotation, and then I'm going to draw it towards my solid here. And so when I draw through my solid, I can see that I'm right in the air, so I already know it's a washer. And I want to go through to the second curve here. Okay, so, and that curve is x equals y to the 1/3. And I want to know what this distance is right here. Well, I know that this distance right here from the y-axis, that distance right there is called x, right? And I know that this distance right here, because I want things in terms of y, is also the same as y to the 1/3, right? And I know that that equals 2 altogether. So I could say that x plus r equals 2, kind of trying that same thing, so that r equals 2 minus x, but I didn't want things in terms of x, I wanted things in terms of y, and I know that x equals y to the 1/3, so r equals 2 minus y to the 1/3. So other people might say, instead of calling that x, they might call that y to the 1/3, that distance right there. Okay, so there's my big R. And then my little r is just this distance right here, just the inner, the air, from the axis of rotation to right there. And you notice that's a solid line. And so that distance actually is always 1, right? That is constant 1. So little r is 1. So I'm going to put these things in my, my formula for my volume. And so let's see here. Our volume is going to be pi. Remember, it's r squared minus r squared, and pi out in front, right, is the formula. So my integral, I have, this is my this is 2 minus y to the 1/3 squared, and then minus, and then 1 squared dy. And my integral is going to go, now I want to know where my radiuses are, and these are all of my radiuses that I would have, and those radiuses go from 0 for y up to 1 for y. So this is where my integral is going to go from. So I'm going to have my radius here, which is a long radius, right, and subtract out the inner, and then the next one, right, and the next one, and the next one, and they're going to go from y is 0 to y is 1. So 0 to 1 happens to be the same bounds as this one up here, but those were in terms of x. Just coincidental that they're the same there. And believe it or not, that both of these things are going to give me the same answer. And so if you go and you're going to have to FOIL that out and integrate it, you can, when you subtract 1, you can combine like terms. Believe it or not, they're going to give you exactly the same answer. So it might not look like it's going to give the same answer, but it is. So you can check that out, and you can tell me if it doesn't give the same answer on both of them. But anyway, so that's that story there. I actually had asked you to solve this one and not just set it up. And then, so now I'm feeling guilty about it. So I'm going to say for you to solve it and tell me what the answer is. And so, because we were supposed to, and make sure that they're the same. And so here is one that, that I had on the test as well, that was set up only. And that's what I did on that last one because I got a little bit lazy. And so, because it was something that was easy to integrate, I want to make sure that I'm integrating the ones where you're going to have that are a little bit harder to integrate. But okay, so this one, we got y equals 4x minus x squared. And so I am not going to be able to solve that for x no matter what. If I did, it's going to cause square roots of y. It's going to be messy. It's going to not be easy. It's going to be something that looks really, really bad. Okay, so they said, what about if you're going around the line x equals -1? So x equals -1 is a vertical line. And they've drawn this curve for me here. And y equals 3. They didn't put, oh, y equals 3. That's x equals 3. Sorry, just checking you. Y equals 3 is right here. So this is what I'm going to be rotating. So the rest of this I can ignore. So I'm going to be rotating that around the y, not the y-axis. X equals -1. So right here is the y-axis. So if I was going to use a disc or a washer, then because it's going around something parallel to the y-axis, this would be dy. So all vertical, if your axis of rotation is vertical, the disc washer is going to be dy, which would mean that my equations need to be solved for x. And they're not. So it would be not okay. I'm not going to be able to solve that easily for x. It's going to be a mess. So, so the shell is what I'm going to have to use because it will be the other dx where my equations need to be solved for y and equals blah blah, and they are. So I have to identify the h, and h is parallel to the axis of rotation. I like to draw that in here, going through your solid. So h goes from here to here. That's a typical h. There's multiple h's. Here's another one over here. It's not as big. And here's one that's nearly 0. And over here, there's one that's nearly 0 as well. Okay, and so now my h is my top curve, which is 4x minus x squared, minus my bottom curve, which is 3. So my h is 4x minus x squared, that's top curve, minus 3, that's the bottom curve. Top curve minus bottom curve. My r is not just going to be x, because I am this distance right here that I'm going to attempt to draw in green from the x-axis to h right there. That distance right there is called x, but that's not what your radius is. From the y-axis to a point is called x. Your radius goes all the way over here, right? My radius is from here to here. That's my radius. And so this distance is called x. This distance is 1. Sometimes people tell me that distance is -1, but distance is not negative. That distance, how far is that, is 1. And so how far is this altogether? Well, you'd go 1 and then plus x more, so it's 1 plus x, or x plus 1. And so there is our radius. They asked us just to set it up. So our volume is going to be 2 pi x plus 1 times 4x minus x squared minus 3 dx. And our heights go from 1 to 3. So 1 to 3. Sometimes people ask me, hey, you know, would it be possible to use symmetry on this? And you have to be really, really, really careful when you use symmetry on these things. And so some of them, my answer is going to be, yeah, you know what, that would work to use symmetry on that. And on others, it won't work. And on this one, if I was going around this axis, symmetry would actually work. But around this axis over here, whipping around, this half of it isn't the same, doesn't have the same radius as this half over here. And so actually, you're not going to be able to use symmetry. Okay, so we set that up. And so I have been changing what method I'm going to use but leaving the problem the same. And this wasn't possible on this problem because there's only one method that was okay on it, and that was the shell. So I have the same problem going there, but you notice what I changed, and that was I changed what my axis of rotation is just to kind of show you. So I kind of have that same deal going here. There's my solid right there. I'm going to put 1 on here because the axis of rotation is y equals -1. And so I just kind of wanted to convince myself, okay, it's 2 of these. So actually I can put it on here. Here it is, y equals -1. Okay, so there's my axis of rotation. And so on this thing, I think now you could use symmetry if you wanted. I don't think I'm going to. I'm just going to, because I'm just setting it up. So I think I'm going to just be happy. So if I'm going to use the disc or the washer, because I'm going around something parallel to the x-axis, this will be dx, which would mean my equations need to be solved for y. And they are. And so the shell would be dy, where my equations have to be solved for x. Or easy to solve for x, and this is hard to solve for x, makes a mess. So it's not actually possible to use the shell. I probably could set it up with a shell, and then I wouldn't be able to integrate it. So it's going to be much easier with a disc or a washer. Now I haven't decided which one it is, a disc or a washer yet, and I don't get to choose that. It is what it is, right? So now what you do is you go to the axis of rotation, anywhere on the axis of rotation. So I can be here, or I could be here, or I could be here. And I usually try to get kind of in the middle. And so I'm going to go not in my usual middle, but I'm going to go, in almost the middle. Oh, that might be my people for a walk. How many problems do I have? I have this one. Tell them I'll go. Oh. Can you tell them that I'll go on the walk? Okay, I'll get ready.
Yeah, she'll be ready.
Okay, so we got to do this problem so I can go on my walk. Okay, so we said that we were going to use the washer method, right? Because I'm in the air here. So it has to be a washer. And this distance from here to there, from the x-axis to here, that distance is called y. And y equals 4x minus x squared. But that's not the whole distance that I'm going to go. I have to go this distance here as well, which is 1. So my capital R, which is all the way from here to there, where this distance is y, which is, it's not the whole way that I want to go, which is, so from the x-axis to the top of that curve is 4x minus x squared. So my radius is 4x minus x squared plus 1. And then my little radius is this distance here. And I'm just drawing a typical one. So that whole pink was R, and now this whole green is little r, is what it is. So this distance right here, and you can see that that distance is constant because that's horizontal, and this is horizontal, and that distance is always 3, right? Because this distance from here to here, wait, is it 4? It is 4, isn't it? This, I was lucky I checked. From here, 0 to 3, right, is 3, and then one more is 4. So that distance is always 4. I almost had that wrong there in my excitement for the walk. So the volume equals pi integral. Remember, it's r squared minus r squared, pi. And so we're going to have here 4x minus x squared plus 1 squared minus 4 squared dx. And then my bounds are going to go from right here, this corner, right? This is where I would have my first of my radiuses would go, right? This radius that I just drew in there represents both big R and little r at the same time. And so that's at 1 and to 3, 1 to 3. And then I would have to, you know, in order to solve that, I would have to multiply that all out, which would write it twice and use multiplication there, 6 multiplies. So it would be kind of a pain to do this here. These will not give you the same answer. And so these two things, even though it looked like the same solid, because you're rotating around a different axis, you're actually going to give different answers. And so I don't think they're going to give us the same answer there. Okay, friends, and so I'm going out for my walk, and that's the end of 5.3. Boy, 5.3 was long. We're not going to do 5.4. We'll be doing 5.5 next.